All right, video number 3 in this lake series. So, pulleys. Okay, we've done a pulley with something on a table and something hanging. We've done a pulley with two things hanging. Now, pulley with something in freehang and something on an inclined plane, no friction. So, as we say, we can need to remember the stuff we've done before. Newton's laws, F equals ma, total force is mass times acceleration, and third law, forces come in pairs. There's always two things acting, never one in isolation. And remember that's one thing, remember our free body diagrams that help think about this. And then in this, like on a coordinate system, to the right will be positive, like on the x-axis. To the left will be negative, like on the x-axis. So here, we got two things connected by a string, provides tension, A and B. And in this problem, when we get to it, we'll have the mass of A is 0.4 kilogram, the mass of B is 0.1 kilogram. And then there's a 30-degree angle there. So, first off, on the thing that's hanging right here, we have tension in the string. We have gravity pulling it down. Okay. Here, tension this way. And we have gravity pulling it down the slope. And it's only the parallel component of gravity. Remember, there's a component. Gravity's partially perpendicular to the plane, but also in the direction, so the parallel. Force of gravity, parallel. I'll just do it that way instead of FG parallel. Less stuff. So this one is an acceleration from these, and this one is an acceleration from these. So if we get our equations, we got, now we're looking at A has a mass of 0.4 and B 0.1. So let's see. And remember, the parallel part in the direction of motion would be sine of 30. So if we write that down, the parallel component, as we've done before, it'll be the mass of A times G times sine of the angle. Okay. The normal component goes to cosine. The parallel component is the sine. We've worked through that and other things. So for this one, I'll leave the formula for now. I'll do it as a formula, and then we'll see. Maybe for some people it'd be easier to put the numbers in right away and do it that way. But I'll do it as a formula first, then with numbers. So, because with the formula, with a lot of letters, it can confuse some people. They don't like it. But put numbers in, it can be easier, especially at first. When you get more advanced in the physics, you're doing a lot of formulas, so you get used to it. But here, numbers might be easier. So I'll do the formula thing first. So here, then we can see what's going on in general. So for this, we have, so remember, this is considered our positive direction, and this is our negative. So t plus negative f is like t minus f. So t minus f parallel is ma times acceleration. The masses are different. but they're attached by the string, so accelerations will be the same. As long as the string, you know, it's got the same tension in it, no kinks or anything. And here, Fg minus T, because that's positive and that's negative, you know, F sub G plus negative T is like Fg minus T. Once I'm doing that, positive direction, negative direction, and that's MB times A. The tension is tension. The ropes is a similar tension throughout uniformly. So we solve for T here. Or we could solve for T and set them equal, or get this one and put it underneath and add the equations. I'll just do it this way. F parallel plus MA A. Move the T over, move this over. You can do the algebra. Get like that. And then the tension's equal, so we put these together. F parallel plus MAA is FG minus MBA. Then if we want to solve for acceleration, in this case, which we're going to do in the problem we're going to do, you know, I don't know, it depends on what you're doing. Maybe you're solving for angles, so you rearrange this differently. I'll show you the acceleration right now. And I'll go back and solve as if we're doing the angle. But then you can solve for other things, of course. And so, if we add this to each side, then F parallel plus MAA plus MBA equals FG. And subtract F parallel. And you can factor A out of here. So I do two things at one time. I'm running out of room. You can do the algebra more slowly if you need to. So we get that, and the divide, and is it showing up? You can still see it. A F G minus F parallel over, running out of room down here, it's hard to write, M A plus M B. All right, so and then if we substitute in for F sub G, I'll cram it over here. So this would be F sub G here. You know, we're talking about for the B, the mass of B times G. Maybe I'll run out of room. I guess I'll push this over to the side. So I have more room to write. I'm not crammed against the wall. So A will equal the mass of B times G, because you know that's what we meant for that thing. Then F parallel was for A, and that's going to be the weight, a component of the weight, which is mg, mass times acceleration due to gravity, times sine of theta. So m a g sine theta over MA plus MB. Okay. And then if we want to rewrite it, we could factor out the G. So we could say A and B minus MA sine theta over, I'll rewrite this, MB plus MA times G. So it's like, oop, computer screen went dark. Get this open again. I need to change the settings so it doesn't go dark every 10 minutes. So, it's like a fraction or multiple of acceleration due to gravity. So, that's what we get, and I'll do that on this. So I'll get this and rewrite it up here so we can use it later, but I'll show you if we solve for something else. Let's see, so acceleration is going to be mb minus ma sine theta over mb plus ma, capital A. Accidentally put a small a there, capital A. And A, G, K. So, I guess I'll do the problem first. Now I'll get this stuff here. I'll solve for theta, then I'll go back and do a problem with this, so I can erase all this stuff. While it's here, instead of solving for A, we got to solve for other stuff sometimes. So, what if we had to solve for, like, G? If we're going to solve for G, you know, it's just A times the reciprocal of this. If we're going to solve for theta, then it could be like, we have, see, we get to this point. Say we want to know the angle. What angle will this happen? So I move this over to this side, and we got F parallel is FG minus MBA minus MAA. And then substitute in F parallel for this one was MAG sine theta equals MBG minus MBA minus MAA. Then we divide by MAG. So sine of theta MBG minus MBA minus MAA over MAG, capital A. Hard to write down here, not much room. Okay, so do we get the angle that way? You know, get this, we'd have to have all this stuff. We'd need acceleration in the masses, and then we could do inverse sine to get the angle. And that would say what angle we need to get this situation, if it would be possible at all. Okay, now we go back to this, we're gonna find acceleration. This is just, again, to show you, we start with stuff, and sometimes we want to get the acceleration. Sometimes we want to get angle. Sometimes we want to figure out what mass we need right here to get a certain thing. So we got to solve for different variables, so we need to know our algebra and be able to work with literal equations. Literal equations, equations with letters. literal of or having to do with letters. Okay, so we have our derivation there. Now we will use our derivation for this particular problem. So we have this. Ta-da, now the board's cleaner. So we'll see what acceleration occurs in this situation. 30-degree angle, those masses, then acceleration will be 0.1 minus 0.4 sine of 30 over 0.1 plus 0.4 times 9.8 meters per second. So sine of 30 is a half. Cosine of 30 squared to 3 over 2. So a half of this is 0.2. So that'd be negative 0.1 over 0.5. 0.5, negative 0.1, but that's just 1/5. So 1/5 of 9.8. 9.8 divided by 5. 1.96. So negative 1.96 meters per second squared. Remember, the negative means to the left. So this is going down. Okay. So there is an example of a pulley on an inclined plane, a little modification we do. And next I'll do pulley inclined plane with friction. All right, cool.